Structures involving more than one kind of material are called heterostructures. Hetero is the Greek word for different. For example, we could be working with different semiconductor materials, such as the alloy semiconductor, aluminum gallium arsenide, in which we can vary the relative amounts of aluminum and gallium. So X is the fraction of the group 3 elements in this material that are the aluminum atom, and 1 minus X is the fraction that are the gallium atom. This is a material that we can make actually with almost arbitrary values of X between 0 and 1. So we can make heterostructures with this material, layers of different concentrations of aluminum in different successive parts of the material. Such changes are made routinely in modern semiconductor structures. There's a large range of structures available to us made with various different materials, especially in so-called 3-5 semiconductors, in which we make such heterostructures with different compositions in adjacent layers. And this allows us to make abrupt changes in material concentration. That happens at the interface between gallium arsenide and, say, aluminum gallium arsenide, for example, with 30% aluminum. In some of the early laser diodes, it happens in all the modern laser diodes made with different materials, such as indium gallium arsenide and perhaps indium phosphide or indium gallium arsenide phosphide, a quaternary material instead. And it also happens when we try to make quantum well structures that involve very thin layers, for example, 10 nanometers thick. And again, those are made with these similar classes of materials, like indium gallium arsenide or gallium arsenide. In fact, modern laser diodes, for example, used in telecommunications, are all based on layers of the order of 10 nanometers thick of indium gallium arsenide between layers of other materials. We can analyze heterostructures using effective mass theory. Note that the effective mass, however, is in general going to be different in different materials. And as a result, it's then better to write our envelope function Schrödinger equation in this somewhat different form. And in this form, we've put the 1 over the effective mass inside the del squared. Now, if the effective mass is not changing between one material and another, it's just a constant, so we could take it outside and we'd have the equation we had before. Here, though, it turns out to be better to push this parameter inside the middle of the del squared. And the reason for doing that is that if we do that, and if this effective mass does change with position, we end up with a better behaved equation. In particular, we don't lose particles, and I'll have something more to say about that particular point. And then with an equation like this, we will also use boundary conditions such as the continuity of the envelope function. Well, that is what we would expect in a differential equation, perhaps. But instead of just continuity of the derivative, or the gradient of the wave function, we'll use 1 over the effective mass times the gradient of the wave function. These will be the two boundary conditions we'll use, and we'll use this version of a Schrödinger-like equation. This particular set of these two boundary conditions and this differential equation here give us a consistent way of handling the situations where the effective mass is changing either smoothly in space or as we go from one material to another. This change in the way we are writing our envelope function Schrödinger equation is another example of our construction of a model. The change we've made in the way we are writing the derivatives, moving the 1 over effective mass term inside the derivative, is something that makes no difference if the mass is the same in all materials. However, if the mass is changing in space for any reason, then the original form of the Schrödinger equation cannot work because particles would not be properly conserved. The operator corresponding to time evolution, as in the motion of some wave packet, would not be unitary. This new way of writing this envelope function Schrödinger equation is something we just make up, but that does restore that conservation of the particles as time evolves. This new way of writing it is not the only way we could change Schrödinger's equation to retain particle conservation, however. This approach is not really something we derive from anywhere. We simply propose it, knowing that it has at least the right basic mathematical properties. This particular approach is consistent with the new boundary conditions we're choosing here. Again, these boundary conditions are to some degree an arbitrary choice, but they also conserve particles. We encounter similar kinds of mathematical phenomena when we look at the boundary conditions we get with light waves as they go from one medium to another, just like light striking a glass window, for example. There also we have to choose boundary conditions in such a way that they conserve photons. In that particular case, we can arguably derive the boundary conditions from Maxwell's equations. In our effective mass case, we cannot really perform such an analogous derivation, and there are other choices we could make instead. One reason why we cannot derive such boundary conditions is that such an abrupt interface certainly violates the assumption that we are dealing with an infinite crystal. So we could even argue that the entire Bloch theorem approach breaks down in such a case. Again, though, we find that using this as a model works apparently well enough in many situations. We are not asserting that this set of equations and boundary conditions is fundamentally correct or even quite justified theoretically. We are saying that we can put together a model using these that seems to work well enough in many situations, predicting experimentally observed phenomena well enough in a wide range of cases. In general, with semiconductor heterostructures, we can draw diagrams like this one here, and we treat the changes in the position in energy of the edge of a band, such as a conduction band, in one semiconductor and another semiconductor as a band offset, which we use in our Schrödinger equation through the potential V. So the position of the edge of the conduction band jumps abruptly as we go from one material to another, and we can model that as an abrupt change in potential V in our Schrödinger equation. And we get a similar behavior in the valence band, and in this case we should look at this upside down. This is a lower energy in this material for the holes in the valence band compared to the energy for the holes here, so we can consider holes with effective masses as well inside these layers, seeing lower energy in this layer compared to that one. These particular jumps in the position of the edge of the conduction band and the position of the edge of the valence band are called band offsets. So here's the conduction band offset, delta EC, and the valence band offset, delta EV. And in practice, these are usually determined empirically. We do measurements to deduce what these numbers are. It's possible in principle to predict them theoretically, but that's quite a difficult calculation, and it's particularly difficult to make those calculations very accurate. When we look at these heterostructures, there are, of course, various ways in which the conduction bands and valence bands in one material could line up compared to the conduction and valence bands in another material. This particular configuration here is called a type 1 band lineup, and in this case the electrons see lower energy in this material, and also the holes see lower energy in this material, because the holes, remember, have to be considered as bubbling upwards. If we stand on our heads and look at this upside down, this is low energy for holes and this is high energy here. So this configuration has lower energy for both electrons and for holes in this material layer, and higher energy for both there. That's called a type 1 band lineup. We could, for example, have a band lineup like this. This does exist in some materials. Nearly all the devices use this kind of band lineup. They use materials that give us these kinds of behaviors as we go from one material to another. And as I said, electrons and holes have the lowest energy in the same material in this case, which usually turns out to be better for devices, especially optoelectronic devices. And as I said, remember that holes bubble upwards in pictures like this.